So good morning to all of you students. Today I am going to explain about the threaded binary tree. So as we know in binary tree basically some null pointers are wasted. So if these null pointers are used to point ancestors then it becomes threaded binary tree. So in nutshell I would like to say that in threaded binary tree basically null pointers are used. So this video basically covers the introduction part, which includes its inventors and then definition of the threaded binary tree, means how we can define it, then from where we have been motivated for this threaded binary tree, because this is basically the modification of the binary tree. So we have some modification in the binary tree. We will see in this modification and then the main characteristics of the threaded binary tree, and then how these threaded binary trees can be represented in memory, like we can use the structure. So we use some more variables we will see in this. Then types of the threaded binary tree, definitely there are normally there are some types like left threaded, right threaded, fully threaded, or we can say we will discuss about the single threaded and double threaded binary trees, and then we will convert the binary tree into threaded binary tree. This is a very important part of the threaded binary tree, that's why I have made it red, these three things. So and then we will inside the node in a threaded binary tree. We will see how the node can be inserted in the threaded binary tree. And then traversing is also very important part, because the null pointers of the binary tree are utilized and they are basically focused on the traversing. So traversing can be done pre-order, in order and post order. And then we will see the comparison threaded binary tree with the normal binary tree and the binary search tree, and then advantage and disadvantages of the threaded binary tree, and finally we will see the application, means where these threaded binary trees can be used. Now we will see the introduction of this threaded binary tree. So Perlis and Thornton, they proposed new binary tree called threaded binary tree, which makes use of null pointers to improve its traversal process, or we can say these threaded binary tree are basically focused on the traversing. And this traversing can be done like pre-order traversing, in-order traversing, and post-order traversing. So in a threaded binary tree, null pointers are replaced by references of other nodes in the tree, or normally they point to the ancestors. So these extra references are called the threads. That's why its name is threaded binary tree. So these threaded binary tree are also a binary tree in which all left child pointers that are null or in linked representation points to its in order predecessor, and all right child pointers that are null in linked list representation points to its in order successor, or we can say all the left child pointers points to in order predecessor and right child pointers points to in order successor. If suppose it is to be noted here, if there is no in order predecessor or in order successor, then it points to the root node. A threaded binary tree can be defined as, it is basically a binary tree, or we can say this is the extension of the binary tree, which is threaded by making all right child pointers that would normally be null point to the in order successor of the node, and all the left child pointers that would normally be null point to the in order predecessor, or we can say in this binary tree all right child pointers basically point to in order successor, and all left child pointers basically point to in order predecessor. The traversal order is the same as in order traversal of the tree. Traversing is same as we normally see in the binary tree. as we have already seen in the binary search trees. However, pointers can instead be added to tree nodes rather than replacing linked lists, thus defined are also commonly called threads, and can be used to enable traversal in any orders desired, like it can be used to enable pre-order, post-order, in-order. For example, we can see the example like a tree whose nodes represent information about pupil might be sorted by name but have extra threads allowing quick traversal in order of birth, birth date, weight, or any other known characteristics. So we can say in such situations these threaded binary tree can be used. Now we'll see why we use threaded binary trees, or how we have been motivated to use this threaded binary tree. So basically binary trees have a lot of wastage space. It has many null pointers, like in all the leaves we have null pointers. The leaf nodes each have two null pointers, and we can use these pointers to help us in order traversal. We can use these pointers for in order traversals, and the threaded binary tree makes the tree traversal faster. If we use these pointers in threaded binary trees, so this makes the tree traversal faster since we don't need stack or recursion for traversal. If we use these threads for the traversing, then we don't use stack or recursion for the traversal. So this is very useful. It also saves our time. So in a 1968 textbook, Donald Knuth asked whether a non-recursive algorithm for in-order traversal exists that could use no stack and leaves the tree unmodified. So one of the solution to this problem, it was tree threading presented by Morris in 1979. In 1969 follow-up edition, Knuth attributed the threaded tree representation to Perlis and Thornton in 1960. So in such a way we can say we have been motivated for this threaded binary tree. Moreover, in many applications, binary tree traversal are carried out repeatedly, which causes the overhead of stack operations. So we can say if we use the recursion, it overhead it causes the overhead of stack operations, and the implicit ones, if this is implicit, the implicit ones carried out by the runtime system when a recursively coded traversal is being executed, and it may be the explicit push pop of a non-recursive but stack driven traversal procedure which is costly in terms of program execution time. So we can say this may be of two type. If this is implicit one, then we need to use the recursive approach, and if this is explicit one, it can be done by using the push pop of the stack, because this will be the stack driven, though it is this may be non-recursive, but this is the stack driven. Therefore we can say, ultimately we can say, it is sometimes useful to modify the data structures of pointers and records which represent the binary tree, so as to, therefore we could speed up, say, the in-order traversal process, make it stack free. So in this way we can ultimately we can say, by avoiding recursion and stack, the use of stack, we can speed up the traversing. So this is the ultimate goal of the ultimate objective of using the threaded binary tree. It is also be noted here that recursion, which uses stack space, and this is proportional to the height of the tree. So this is also the reason, that's why we use the threaded binary tree. The main features of the threaded binary tree. So as we know that all the null links of the threaded binary tree are used to store the reference of successor and predecessor or ancestors in order, pre-order and post-order, so that it can be traversed without using extra data structure like queue and stack. because we utilize the null links of the threaded binary. That's why we don't need to use extra data structures like queue or stack. This is the first benefit of using the threaded binary. And the second benefit is the threaded binary tree is the data structure where each node is on a binary tree. Each node is on a binary tree, and at the same time we are also dealing with the linked list at the same time on a linked list. So one node, each node is on a binary tree as well as on the linked list. So this turns out to be extremely useful if you need to access the data in multiple dimension. If you want to access the data in multiple dimension, then it is better to use, it is good to use threaded binary tree. And the third feature is a binary tree can give an efficient search function based on the key. It can give the good search function, while the linked list may be used to store other relationships, such as the ordering of the last update. So we can say this is the combination of the binary tree and linked list, which can provide some different type of features, like to store the relationship. You will see the representation of threaded binary tree in memory. Means how we can represent the threaded binary tree in memory. So the structure of a node in a threaded binary tree, it is slightly different from that of a normal binary tree because it contains some other variables too. Unlike a normal binary tree, apart from left pointer, right pointer, and info, each node of a threaded binary tree, it contains two extra pieces of information, which is namely left thread and right thread. So apart from this left pointer, right pointer, and info, this threaded binary tree also includes left thread and right thread. The left and right thread fields of a node can have two values. It will normally have two values. This will include one. This one indicates a normal link to the child node. If this is one, it means this will indicate a normal link to the child node. If it is zero, it indicates a thread pointing to the in-order predecessor or successor. Or if it is zero, it will indicate a thread that will point to its ancestor. And this is the figure which is showing the structure of a node. Like here we in middle, this is the data, this is the actual information of the node. Here this is the address of left child, this is left thread, this is address of right child, and this is right thread. So this is the structure of the node in a threaded binary tree. Coding, we can use a structure like we normally do in case of normal binary tree. We can use a structure. So in threaded binary tree, it will include a left pointer, right pointer, uh, info variable, and then a character variable. This will store a thread variable. So we can use left, right pointer, info, and thread. It is to be noted here that we have used a char field thread as a tag. The character 0, this is used for the normal right pointer. This will use 0. 0 is used for the normal right pointer, and 1 is used for the thread. If we are using the thread, it means it will use 1, and if we are using the normal right pointer, it will use 0. So if we talk about the operations of the threaded binary, we deal with the four operations. First one is inserting node into binary tree. We will insert the new node in the existing binary tree, and then traversing or printing the tree. Here we will see the main advantage of threaded binary tree. And then third one is deletion of element. We can delete the element in threaded binary tree, and deletion of the tree itself. So these are the four operations, but we will focus only on these two. So first we will focus on the traversing, and then we will see the how we can insert a node in the threaded binary tree. So if we talk about the types of the threaded binary tree, there are basically two main types. First one is single threaded binary tree. This is also known as one way threaded, and second one is double threaded binary tree, or this is also known as two-way threaded or fully threaded. If we talk about the single threaded binary tree, in this single threaded binary tree, each node is threaded towards either the in order predecessor, this is also known as left threaded, or successor, in order successor, or this is right threaded. Means all right null pointers will point to in order successor, or all left null pointers will point to in order predecessor. Means, or we can say these null pointers will point to the ancestors. These ancestors may be in order predecessor, or this ancestor may be in order successor. And second category is double threaded. Means the null pointers can be used in simultaneously. Both the pointers, left as well as right pointers, can be used. So this is known as double threaded. This is also known as two-way threaded or fully threaded. In this, each node is threaded towards both the in order predecessor and successor. It means it is left threaded and right threaded simultaneously. Means all right null pointers will point to in order successor, and all left null pointers will point to in order predecessor. Now we'll see the right threaded binary tree. In right threaded binary tree, all the right null pointers point to its in order successors. Like in this figure, in this tree, we can see the node F, H, G, D. Their right null pointers are pointing to their in order successors. Like if we see this node F, its right null pointer is pointing to in order successor, which is B. This G, its right null pointer is pointing to its in order successor, which is A. Its successor is A. And the right null pointer of H, this is pointing to G because its in order successor is Z. In the same way, this right null pointer of D, this is pointing to C. It is to be noted here that this X, this particular X, this is also null pointer. They are the extreme rightmost null pointer. It is not pointing to any in order successor because it is not having any in order successor. So we will see later that to where it will point. Basically, it will point to the dummy node. So the concept of the dummy node we will see later. So this is the left threaded binary tree. In left threaded binary tree, all the left pointers point to in order predecessor. Like in this binary tree, we can see the left null pointer of this node H. It is pointing to its in order predecessor, which is node B, and the left null pointer of node D, this is pointing to its in order predecessor, which is node A, and the left pointer of node E, it is pointing to its in order predecessor, which is node C. It is to be noted here that the left pointer of this node F, this is not pointing to its in order predecessor because it is not having its in order predecessor, because the leftmost null pointer and the rightmost null pointer, like this, they don't have in order predecessor and in order successor respectively. We will see this case later when we will discuss about the dummy node. Now we will discuss the double or two-way threaded binary tree. In two-way threaded binary tree or double threaded binary tree, all the left null pointers point to in ordered predecessor and all the right null pointers point to in ordered successors. Like in this figure, in this binary tree, we can see the right null pointer of this node F, it is pointing to its in ordered successor, which is node B, and the left pointer of this node, left null pointer of node H, is pointing to its in order predecessor, which is node B. The right null pointer of node H, this is pointing to its in order successor, which is node G. The right null pointer of node G is pointing to its in order successor, which is node A, and the left pointer of node D is pointing to its in order predecessor, which is node A. In the same way, the right null pointer of node D is pointing to its in order successor, and the left null pointer of node E is pointing to its in order predecessor. So it is to be noted here that the left null pointer of node F is not pointing to any node, to, no, to any ancestor. In the same way, the right null pointer of this node E, it is also not pointing to any ancestor, because the left null pointer of leftmost node, it is not having any in order predecessor. In the same way, the right null pointer of rightmost node, that is E, it is also not having any in order successor. We will discuss these two cases of this null pointer, right null pointer of node E and the left null pointer of this node F, when we will discuss about the dummy node. Apart from the in order threaded binary tree, we have two more categories of these threaded binary tree. The fourth one is, or we can say, this is the fourth category. This is pre-order threaded binary tree. So in this pre-order threaded binary tree, all left null pointers point to pre-order predecessor and all right null pointers point to pre-order successor. In the same way, in post-order threaded binary tree, all left null pointers point to post-order predecessor and all right null pointers point to post-order successor. So these two categories are also there. They are also not so much popular as the in order threaded binary tree is popular. So, and these two categories are rarely used in threaded binary trees. A simple binary tree into the threaded binary tree. So this is the example of a binary tree that is containing the nodes like A, B, C, D, E, F, G, H, I, J. Now we will see how this binary tree can be converted in the threaded binary tree. But we have to note here that like if we focus on this particular node, so this is the left pointer and this is the right pointer. So both the pointers are engaged here in this point in this node B2. Left and right pointer both are engaged. Here in D, both pointers are engaged, left and right pointers. But we have to see for those nodes which are having null pointers, like this particular node H, it is also having a left null pointer, right null pointer. I is also having left null pointer, right null pointer. E is also having left null pointer, right null pointer. This F node, it is having a left null pointer, but right pointer is pointing to a child, that is node J. In the same way, C is having left and right child F and G. G is also having the left null pointer and right null pointers, or we can say all the leaf nodes have the left as well as right null pointers. So H, I, J, G, they are the leaf nodes. That's why definitely it will have left as well as right null pointer. Moreover, E, this is also having the left null pointer and right null pointer, and this F is also having left null pointer. Now we will see can be converted. To convert the above example, or we can say to convert the above binary tree, this is shown here in the left top corner. uh, into a threaded binary tree, first find the in-order traversal of this tree. So the in-order traversal of this tree will be, this is H, D, I, B, E, A, and then F, and then J, then C and G. We can also see it from here, like the in-order traversal will be, this is H, D, and then I, then B, then E, then A, and then F, and then J, then C, and then G. So this is the in-order traversal of this binary tree. Now when we represent the above binary tree using linked list nodes H, I, H, I, E, F, J, and G, they are the left child pointers are null. So we can see that the left child pointers of these nodes like H, I, E, F, J, and G, it is null, and these null pointers are replaced by address of its in order predecessor. So they can be used to point the in order predecessor, like I is used, I can be used to point to D, E can be used to point B, F can be used to point A, and J can be used to point F, and G can be used to point C. So the left pointers of I, E, F, J, and G can be used to point in order predecessor. But here the node H means this particular node does not have its in order predecessor, because we can see from this diagram, so it is not having any in order predecessor, so it points to the root node, or we will see the concept of the dummy node, it will point to dummy node. In the same way, the nodes H, I, E, J, G, they have right child pointers, and they are null. So these null pointers are replaced by address of its in order successor respectively. So H will point to D, I will point to B, E will point to A, and J will point to C. It is to be noted here that the node G does not have its in order successor, so it points to the root node A. Now we will follow the steps to convert from binary to threaded binary tree. So step 1 is keep the leftmost and the rightmost null pointers as null. Means we have to keep all the leftmost and the rightmost null pointers as null. In this binary tree, the leftmost node is, this is H, and this the rightmost node, this is G. So we have to keep the left null pointer of this node H null and the right null pointer of G null. And the second step, change all other null pointers as, all the left pointers point to in order predecessor, and all the right null pointers point to in order successor. Like here in this binary tree we can see, if we consider all the left pointers like this, the left pointer of node I, it is pointing to node D, this is in order predecessor, and the left null pointer of node J, it points to its in order predecessor, which is node F. In the same way, the left null pointer points to node C, which is the in order predecessor of G. In the same way, the left null pointer of this E, it points to node B. So we can see in this binary tree all the left null pointers of like this I, E, F, G, and J, they are pointing to the their in order predecessors. Now we will point all the right pointers, like the right pointer of this node I, this is pointing to its in order successor, which is node B. The right pointer of node E is pointing to its in order successor, which is node A. The right pointer of node J is pointing to node C, which is its in order successor, and the right pointer of this H is pointing to its in order successor, which is D. Moreover, the left null pointer of H remains null. It is shown by X, and the right null pointer of node G, it also remains null. It is also shown by X. So in this way we can see here one more thing. It is to be noted here that in this the particular node has three fields. It has three fields, one for the data itself and other two for the left and the right pointers. But the question arises here that if we talk about the left and the right pointer, how we will come to know that which pointer points to its child and which pointer points to its ancestor. So this is the problem that we will solve in the next slide. So we will see how we can solve. So for that we will require 5 fields for a node. So now let us see how it can be done. Now we'll see how this conversion can be done. So this is the node structure in which we will have 5 fields. This middle field is for the data, and this is for the left flag, and this is the right flag. This is left pointer, right pointer. So we can say it will have 5 fields. First for left pointer, second one is for left flag, and then data, then right flag, then the right pointer. It is to be noted here, this left flag may be either 1 or 0. If this left flag is 1, it means the particular node has a child, and if it has 0, it means the particular node has ancestor. This may be in order predecessor or it may be in order successor. In the same way, this is the right flag, and if it is 1, it will have a child, and if it is 0, it will have an ancestor. It may be in order predecessor or in order successor. And this is the normal right pointer, and this is the normal left pointer. Now we can see here, we'll see here, because this is the root, this is the root node, this is A. So this is simple conversion from this binary tree to threaded binary tree. In this we are having now 5 fields. So this is node A, and the left hand side, this is 1. It means it will have a left child. This is node B, and at the right hand side, this is 1. This right flag is 1. It means it have a child. This is node C. In the same way, node B, it is also having 1 on the left hand as well right hand side. It means it is having a left child as well as right child. Node C is also having a left child as well as right child, because it is having 1 on the left hand side and 1 on the right hand side. Now we come to this node D. At its left, this is 1. It means it is having a left child. This is node H, and at the right hand side, it is having a child. This is node I. Now we come to E. At the left hand side, this left flag is 0. It means it is having a in order predecessor. It means it is having a ancestor, and this ancestor is, because this is the left pointer, that's why it is pointing to node B, which is the in order predecessor. In the same way, it is the right flag is 0. It means it is having some ancestor, and this because this is the right pointer, that's why it is pointing to node A, this is the in order successor. Now if we consider node F, its left flag, this is 0, it means it is pointing to in order predecessor. It means it is having ancestor. This is node A. At the right hand side, this is 1, it means it is having a child. This is node J. If we see this node G, at the left hand side this is 0, right hand side is also 0, the left hand side this is 0, it means it is having an ancestor, and this is in order predecessor. This is node C. At the right hand side, it is to be noted here, or we will see that earlier in the previous slide, this was X, this was null pointer because it was not having any uh, in order successor, that's why this was null. But here this will point to some other node, and this node is known as the dummy node. This is the dummy node, and basically this dummy node doesn't contain any data, but at the left hand side this contains 1, at the right hand side it also contains 1. The right hand side means it has a child, but its right pointer points to itself. It points to itself. At the left hand side also 1, it means it has a child. So the left child of this dummy node will be the root node of the tree. So the left child of this dummy node is, this is A. So this is very important point. This is dummy node. In the same way, now we can see here, this is the leftmost node. At the left hand side this is 0, it means it is also having ancestor. So earlier in previous slide this was null because there was no in order predecessor, but now this pointer will point to the dummy node. It means it is having the ancestor, and this will have the in order predecessor, which will point to the dummy node. So these 2 points this are very important. In the same way, now we can see this I is having a at the left hand side this is 0, it means it is having a ancestor. So this is pointing to node D, which is the in order predecessor, and this is the 0, it means it is also having the ancestor. This is the right pointer will point to node B, this is the in order successor. And in node J, it is on the left hand side this is 0, it means it will point to node F, this is the in order predecessor, and its right pointer will point to node C, this is the in order successor. So in this way we can see that how this binary tree can be converted in threaded binary tree. So one important point, one important node which is added here, this is the dummy node. So, and this is the structure of the node. We can make a structure for this. This is char data int left flag, int right flag, and then the left pointer or the right pointer. So we have seen the importance of this dummy node. Now we will elaborate it that why we need this dummy node, as we usually see that leftmost reference and rightmost reference pointers has nowhere to point because they were not having in order predecessor and the in order successor. Hence we need a dummy node, and this node will always present even when tree is empty. Moreover, in this dummy node we will put right bit or right flag goes to 1 if this is 1, if this right flag is 1, and its right child will point to itself always. It means its right child will point to itself always, like here in this figure we can say this is the structure of dummy node. At the right hand side this right flag is 1, and its right child, this will point to itself always. And if left bit or left flag this is 1, this is 1 here in this dummy node, it means its left child will point to the root node of the threaded binary tree always. Like this is 1, it means it will have a child, and the child of this dummy node will be the root of the threaded binary tree. Like in this figure we can see the left child is the root of the tree. This is node A here, this we have taken from the previous binary tree. So in this way we can see that why we need the dummy node. Dummy node plays a very important role, and from this dummy node it is very much clear that these ones are representing to what. Now we will see its first important operation, which is the traversing. As we normally focus on the traversing in threaded binary tree, or we can say this is the important operation of the threaded binary tree. Now we can say traversing the threaded binary tree, it is quite easy. No need of any recursion or any stack for storing the data. As we have mentioned earlier also, that we don't use any recursion or stack for storing the node. For traversing the threaded binary tree, follow the steps given below. Step 1, just go to the leftmost node in the tree and then print it and follow its right thread. Step 2, if we follow a thread to the right, if we follow a thread to the right, we output the node and continue to its right. Step 3, if we follow a link to the right, or whenever right thread equals to false, then go to the leftmost node in the left subtree and print it and continue. This is important step. Whenever we find the right thread, this is false, it means we have to go to the leftmost node in the left subtree, and then we will have to print that particular node and then continue. Now we will understand this in order traversing, or traversing with the help of example. This is threaded binary tree, which is containing nodes like 6, 3, 8, 1, 5, 7, 11, 9, 13. It is having some uh, left arrows and some right arrows. It means it is having some child and also having some dotted arrows. These dotted arrows are basically ancestors, and these solid arrows, they are the child, they are showing the child. So we have already explained about this the children and the ancestors in detail. Here we will see how we can do the in-order traversing. So we will start at leftmost node and we will print it. The leftmost node is 1 of this threaded binary tree, so we will print it. This, here we are displaying the output. This is 1. The right, follow the thread which is to the right. So if we follow this thread, so this is 3, or this, the right pointer or this thread points to the node 3, because this is the in order successor. So we will print 3. Now we will follow the link to the right, and the link to the right of 3, this is going up to 5, and after following this link we have to go to the leftmost node and then print. So this 5 is the right child of this node 3. So this is the right node and there is no leftmost node, so this is the only node, that's why this 5 will be printed. So this is the output be given, this is 5. So this is very important point here. Whenever we will follow the right link, we have to reach up to the leftmost node, and after that we have to print. Follow the thread, we will follow this thread, so it points to 6 and this 6 will be printed. The link to the right, this is shown by a red arrow, so we will follow this link to the right and we will go to the leftmost node. This very important point here, because it is containing 3 nodes here. We are coming here and we are, after this coming here we are following the link to the right and then we are going to the leftmost node and then we are printing. That's why we will print 7, not 8. 7 will be printed. So this is printed here. from 7 we will follow the thread which is to the right. So this thread is pointing to the node 8. So 8 will be printed. Now to the right. So from 8 we will go to 11 and then we will go to 9 because this is the leftmost node. So it means we are following the link to the right of 8 and we are going to the 9 which is the leftmost node, and then we will print it. So 9 will be printed here. So now we are getting the output. This is 1 3 5 6 7 8 and 9. Now we will follow the thread which is pointing to 11, which is the in order successor. So after pointing this we will print it. 11 will be printed. We will follow the link to the right of 11 and we will go to the leftmost node and print. So this is 13. 13 will be printed. So this is the traversing. So we have visited all the nodes. As we know, traversing means we have to visit all the node at least once. So this traversing is completed because we have visited all the nodes like 1 3 5 6 7 8 9 11 and 13. Now after the traversing we will see another important operation of the threaded binary tree, which is insertion. So insertion in threaded binary tree, this is similar to insertion in binary tree, but we will have to adjust the threads after insertion of each element. So this is very important point here in case of threaded binary tree, that insertion of each element we have to adjust the threads of the node. Moreover, insertion will be quite similar to insertion in binary search tree. So it will follow the rules of the binary search tree also, like as soon as we insert the node in the tree, in the threaded binary tree, we will compare it with the root. If it is less than the root, it will go to the left subtree, or if it is greater than the root, then it will be inserted to the right subtree. So this will follow the simple rules of the binary search tree, but we will have to make some modifications, few modifications, like to insert a node, our first task is to find the place to insert the node and take current equals to root and start from the current and compare root.data with n. N is the node to be inserted, and always keep track of parent node while moving left or right. So these are some modifications. If current.data is smaller than the node, that means we need to go to the right of the root. It means we have to go to the right of the root while going into the right subtree. Check right thread for current node, means right thread is provided and points to the inodal successor. If right thread equals to false, then and current reaches to null, just insert the new node here. Else if right thread equals to true, if this right thread is true, then we need to detach the right pointer. So if it is true, we need to detach the right pointer first and store the reference new node. Right reference will be point to it of current node and make it point to the new node and make the right reference point to store reference. Now we will discuss basically three cases in this insertion. This is case 1, when the insertion in empty tree, the tree is empty and we are going to insert a node. So in this case both left and right pointers of temp is, let us say, a new node. So this temp will be set to null and new node becomes the root. So this new node will become the root in this case, and this root is assigned the temp, and temp left is null, temp right is also null, both are assigned to null. For example, insertion of 16, this is shown in figure, like this is the newly inserted node, this is the only node. So this is the left pointer is null, right pointer is also null. So this is case, first case. So this is case 2. In this case, when new node is inserted as the left child, so after inserting the node at its proper place, we have to make its left and right threads points to in order predecessor and successor respectively. So the left and right threads of the new node will be in after inserting the left and right thread will be temp left will be parent left and temp right will be parent. But before insertion, the left pointer of parent, it was a thread earlier, but after insertion, now it will be a link. So earlier it was a thread, but now it will be a link pointing to the new node. In this way, like parent left thread, this is false, and parent left, this is temp. We can see it on the next slide. With the help of the diagram, we will understand how it happens. Here, this is any example. This is fully threaded binary tree, which is containing the nodes like 20, 10, 30, 5, 16, 14, 17. The in-order traversal in order will be this 5, 10, 14, 16, 17, 20, 30. So it is having the links as well as threads. Like this is the link, this is left link, which is pointing to the left child, which is node 5. This is also link, but this is thread. This thread is pointing to its in order predecessor, which is node 10. And here this is X. This is basically null pointer. This is the leftmost node. It is not pointing anywhere because it is not having the in order predecessor. In the same way, the right pointer of this is also null pointer, which is not pointing to any in order successor. So these are shown by X. Now we will insert 13 in this threaded binary tree. We will insert 13. So as per the rule of binary search tree, it should be on the left hand. It should be inserted on the left hand side as a left child of this 14, because this 13 is less than 14 and it is greater than this 10. Now it will be inserted in this way. When we will insert this 13 here, now it is to be noted here that the left the left pointer, or we can say, it is already having a thread. So this thread should be freed first. So this will be removed, this thread will be removed, and now this will become a link like this. So the thread earlier, this 14, the thread was pointing to its in order predecessor, which was 10. So it is removed here and now it become a link. So, and this link is pointing to its child, which is 13 now. Now we will see, after inserting this 13, we will update the thread of this 13. So its null pointer, left null pointer, will now point, because it will be thread, so it will point to its in order predecessor, which is node 10, and its right thread, it will point to its in order successor, which is now 14. So this is important point here, because after insertion of 13 we are updating the thread. So this is the explanation here, like predecessor of 14 becomes the predecessor of 13. So left thread of 13 points to 10 now. Successor of 13 is 14, so right thread of 13 points to 14. The left pointer of 14 is not a thread now, it points to left child, which is 13. When new node is inserted as the right child, now the node is inserted in the right subtree, or this is inserted as the right child. The parent of temp is its in order predecessor, and the node which was in order successor of the parent is now the in order successor of this node temp. So the left and right threads of the new node will be now, the temp left will be parent, temp right will be parent right, and before insertion the right pointer of parent was a thread. So before insertion the right pointer of the parent was a thread, but After insertion, it will be a link. So earlier it was a thread, but now after insertion, it will be a link pointing to new node. It can be shown like this. Parent write thread will be false. Parent write will be temp. We can see it with the help of the figure. In the next slide, we are considering the same threaded binary tree, which is a fully threaded binary tree. Now we are inserting 15 because 15 is greater than 14 and less than 16. It means this will be the right child of this 14. Now we can see here one thing which is important here, because as soon as we insert this 15 here, so this is already occupied, this right, it is having a thread and which is pointing to 16, its in order successor. But as soon as we insert this 15, so it will be freed here or it is removed here, this thread will be removed here, and now it will be converted in the right link like this. So this thread is removed which was pointing to this 16, now it is removed and now it is a link to 15. Now after insertion we will update the thread of this 15, so its left pointer, or we can say its left null pointer, that will become thread now. So this thread will point to its in order predecessor, which is 14, and the right thread will point to its successor, which is node 16. So in this way its threads of 15 will be updated. So this is the insertion and this is the explanation of this insertion. So successor of 14 becomes the successor of 15. So right thread of 15 points to 16 and predecessor of 15 is 14. So left thread of 15 points to 14 and the right pointer of 14 is not a thread now, it points to right child, which is 15. Now we'll discuss about the time complexity of threaded binary tree. The time complexity of traversing in a threaded binary search tree, this is order of n, where n is the number of nodes in the tree, because we in traversing we have to visit all the nodes. So the time complexity is order of n. And for insert operation, the time complexity of threaded binary tree, this is also order of n because it follows the simple rule of the insertion as we follow in the case of binary search tree. Now we will see the comparison between the threaded binary tree and normal binary tree. If we talk about the threaded binary tree, the null pointers are used as threads in threaded binary tree. In normal binary tree, null pointers remains null. In threaded binary tree, use of null pointer is an efficient way to utilize computer's memory. In normal binary tree, as null pointers cannot be used, hence this is the wastage of memory, because in normal binary tree we don't use the null pointers. This is the wastage of memory. This is important point. Third one is, in threaded binary tree, traversal is easy and completed without using a stack or recursion. But in case of normal binary tree, traversal is not easy and completed using the recursion. In case of threaded binary tree, the structure is complex. In case of normal binary tree, the structure is less complex, because in this threaded binary tree we also use some variables for threads. Fifth one is, insertion and deletion take more time in case of threaded binary tree, but in normal binary tree insertion and deletion takes less time. So this is the comparison between the threaded binary tree and normal binary tree. So this is the comparison between the threaded binary tree and binary search tree. We can have a threaded binary search tree, or any binary tree can be threaded. We can use these threads in any binary search tree or in any simple binary tree. The advantage of threading a binary search tree is that you can easily traverse forward and backward from any node. This is the main advantage of using threading in the binary search tree. That is very difficult to do with a non-threaded binary search tree. We are not using the threading in binary search tree. This forward and backward is not possible. So in fact, a binary search tree, this is a concept that has nothing inherently to do with how the tree is implemented, while a thread tree is only about how trees are implemented. That is to say, how you set up the pointers in the tree nodes. And finally, a binary search tree can be a threaded tree if you decide to implement it that way. So these are the comparison between the threaded binary tree and the binary search tree. So these are some advantages of threaded binary tree. By threading, we avoid recursive method of traversing a tree, which makes use of stacks and consume a lot of memory and time. So the use of stack and use of recursive methods can be avoided by using the threaded binary tree. This is the first benefit. Second benefit is non-recursive pre-order, in-order and post-order traversal can be implemented without a stack. So along with the in-order, we can also use pre-order and post-order traversal. It can be implemented without a stack. Third advantage is backward track is possible. And the fourth one is the node can keep record of its route because we use in-order traversal. So we can keep the record of its route. And the fifth advantage is by changing the null lines in a binary tree to the special links called threads, it is possible to execute traversal, insertion, and deletion, and without using either a stack or recursion. So these are the five advantages of threaded binary tree. So in this way, it is useful. So these are some drawbacks of threaded binary tree. The first drawback is this makes the tree more complex as insertion and deletion operation become more difficult. So insertion and deletion in threaded binary tree are more difficult. And second is more prone to errors when both the child are not present. It becomes erroneous when both the child are not present and both values of nodes pointer to their ancestors. And third one is memory required to store a node increases. So this memory which is required to store a node, it increases in case of threaded binary tree. Each node has a store. Each node has to store the information whether the links is normal links or threaded links. For these normal links as well as threaded links, extra memory is required. So this is also the drawback of threaded binary tree. And the fourth one is implementing threads for every possible node is complicated. So the implementation for every possible node is complicated. So these are some drawbacks of the threaded binary tree. So we have some advantages as well as some drawbacks too. So finally we will discuss some applications of threaded binary tree. The idea of threaded binary tree is to make in-order traversal faster and do it without stack and without recursion. So to make in-order traversal faster without the stack or without the recursion, we can use threaded binary tree. And second application is it is also possible to discover the parent of a node from a threaded binary tree without explicit use of parent pointers or a stack, but it will become slow. So it can also be used. We can discover the parent of a node from threaded binary tree. And the third application is it can be useful where a stack space is limited or where a stack of parent pointer is not available. So it can also be used to find the parent pointers via DFS. And the last application, or we can say some other applications of threaded binary tree are like we can use it in game tree, expression tree, decision tree. It can be used. So these are some applications of the threaded binary tree. So thank you very much for watching this video. In this video we have covered the complete threaded binary tree, and we have seen the definition of the threaded binary tree and the types of the threaded binary tree, why we need it, and we have also covered the important operation, that is the conversion from binary to threaded binary tree, and then traversing and insertion, how we can insert the node and then We have also seen the advantage, disadvantage, and finally we have discussed some application. I hope you would be benefited from this video. Thank you.